Notes 4.2, Part 2, and it continues. All right, let's consider the exponential function y equals 5 to the x. Then the equation for the inverse, if we were to switch x and y, would be x equals 5 to the y. All right, so that's an equation for its inverse. But we don't like to call an inverse function of an exponential x equals 5 to the y. So we rewrite it in the log form, y equals log base 5 of x. All right, so we started to look at this in the previous lesson. So reminding you that this is the exponential form of the inverse, and this is the log form. So these two equations represent the same inverse graph. It's just that we typically call the inverse by this name right here. All right, consider y equals 8 to the x. Then the inverse is x equals 8 to the y by switching x and y. We don't like that exponential form because y is in the exponent position. So we conveniently call the inverse y equals log base 8 of x. Exponential form and the logarithmic form. Again, both these equations represent the same graph. All right, continuing. The following are equivalent equations to each other. Y equals log base 8 of x and x equals a to the y. Notice that we can look at this equation right here and change it quickly to the exponential form by locating the base of a, taking it to the y power, and setting it equal to x. All right, therefore, if we have this equation, 2 equals log base 3 of 9, and we want to change it to the exponential form, we locate the base on the log, which is the base on the exponent. We raise it to the second power and set it equal to 9. So changing from log form to exponential form, identify the base on the log, raise it to this exponent, setting it equal to the value of 9. All right, what if we have an exponential equation and we want to change it to its equivalent log equation? I typically start with the exponent 3 and set it equal to 3 equals log base 5 of 125. So the base of 5 on an exponential has to be the base on a log function. All right, some of our work is going to involve writing the log equation in exponential form. So how do we get rid of the log equation and change it to something that's equal? The base of 6 on the log is also the base of 6 on the exponential. 6 squared equals 36. We know that's true, so we must have changed forms correctly. All right, for this next bottom example, let's get rid of log, putting it in exponential form. So 32 is the base. We raise it to the 2/5 power, and that equals 4. You can confirm this is correct by going to your calculator and taking 32 and raising it to the 2/5 power and noticing that the answer returns as 4. All right, let's change this to exponential form. So 7 to the negative 2 would equal 1 over 49. That confirms in my brain because negative 2 as an exponent would drop 7 to the denominator with 1 on top, and 7 squared, when the negative 2 becomes positive 2, 7 squared is 49. All right, changing to exponential form, 2 raised to the 1/2 power is square root of 2. And this just confirms that 1/2 as an exponent is equivalent to the square root. All right, let's go the other way. Let's change exponential equations to log equations. For me, what I do is I start with the exponent. 1/4 equals log base 81 of 3. you can just double check real quick by changing it back to the exponential form that 81 raised to the 1/4 power is 3. So this exponent is actually, this exponent of 1/4 is actually a log expression. And a lot of times you'll hear that. You might hear that the exponent is a log. The exponent on an exponential equation is a log. And that's why. All right, for this example, let's change it to a log equation. I start with the exponent. A equals log of, I need a base, that base is g, of 4. Change to a log equation, start with the exponent, -2 equals log base 6. If we have a base 6 here, it's a base 6 on the log of 1/36. Last example of changing forms, 4 equals log base 2 of 16. So the exponent is actually a log. 4 is equivalent to a log expression. All right, let's look at some log properties. Okay, for the first log property, it says that log base a of 1 is equal to 0 because, well, let's write this in exponential form to see if that reveals why. If I change this to exponential form, I would start with the base of a, raise it to the 0 power. That would have to be set equal to 1. And that is actually true because anything to the 0 power is equal to 1. Property 2. Why is it true that the log base a of a equals 1? Well, changing this to exponential form verifies that it's true, because when I change it to the exponential form, a, the base, raised to the 1 power, is supposed to equal this value right here of a. And that's true. I don't have to show the 1. It's understood. All right, property 3. Okay, it says that if I have a log with base a, but then I have an expression in here that has the same base to an exponent of x, if I have an exponential in here, these two bases basically are undoing each other. So a log with base a undoes an exponential with base a, and I'm going to get an answer that's equivalent to whatever that is right there. And in this problem, it's x. So this verifies that log functions and exponential functions are inverses of one another. All right, so why is this equal to x right here? Because an exponential with the base of a raised to a log function with the same base a, these two undo each other and you're left with x, or whatever that happens to be. All right, property 4. Okay, notice that we have an equation and we have log on both sides. Well, notice that the logs both have the same base a. Well, what I can do is I can undo log of base a, since it's on both sides of the equation, and this is going to reduce down to x equals y. So whatever is in here is equal to whatever's in here. We're going to use these 4 log properties and our previous work earlier to answer these next few questions on the back. All right, we're going to start out trying to answer all these questions without a calculator, but if we feel like we can't get any further with the problem, then we're going to involve our calculator. We'll talk about confirming using the calculators, and I'll remind you about some keystrokes to do so. All right, so what is this answer? Well, notice that the base on the log is 4, and this value right here is 4. If I put this 4 to the understood exponent of 1, okay, property, I think it's property, which one is it? Let me go back to it. Property 2. Property 2 is the property we're going to look at. Tells us that this answer right here is 1. Base of 4 on the log, a base of 4 on the exponential right here, undo each other. Logs and exponentials with the same base undo each other. We're left with what's in the exponent position of 1. If we wanted to show our work that got us that, here's what you could do. You could actually say, well, that's equal to some x. Let's change from log form to exponential form. So that means 4 raised to the x power is equal to this expression right here, 4 to the first power. If I have the same exponential bases, they drop out, and the resulting equation is x equals 1. That confirms my answer is 1. Okay, so let's look over here. We have a log, base 5, an exponential of base 5. These two are going to undo each other, and actually our answer is a variable, and it's x in this case. Another way to think about that is, from the very beginning, I could have set this equal to some unknown x, change from log to exponential form. This base of 5 raised to the x power is equal to 5 raised to the x. That just confirms that x is my answer. Okay, and this is actually an example of, I guess, property 3. Okay, example 3. That most closely looks like, when you look at properties, again, property 3. The second part of property 3. So what's this answer? Well, 7 is an exponential. Its exponent is log with the same base, 7. So these two must undo each other, so my answer is 14. All right, let's talk about confirming with the calculator, because that was part of the instructions. Okay, how would you type that into the calculator to see that your answer is 1? Hit the green key, alpha, go to Window, and choose option number 5. It's a log template. You can insert everything, and your answer would be 1. All right, problem number 4. It most closely resembles property 1. If you look back at property 1, it says this answer is 0. If you can't remember the properties, no worries. This is what you can do. Set that equal to some number x. Write the exponential. 6 raised to what power is equal to 1? Well, the only way I can get 1 as an answer is if my exponent x is 0. Number 5. All right, I don't really see a property that will help me with this, so I might want to set this equal to x. Convert to an exponential equation. 5 to the x is equal to 1 over 125. I'm still at a loss as what to do, but part of our future work is going to involve getting a like base. Think about 1 over 125. Think about 125 as being 5 cubed. Keep 5 to the x. Bring up 5 cubed to 5 to the negative 3. Same bases, we can equate the exponents, drop the bases out, so we're really just going to solve x equals negative 3. There's nothing to solve. X is by itself. My answer is negative 3. So look back at that problem. We set it equal to x. We changed it to exponential. I noticed that 125 was a power of 5. I rewrote it that way with it being in the denominator. I brought it up to the numerator so I have the same bases. The same bases drop out. X equals negative 3 is my answer. All right, example 6. 10 to what power is 10,000? Because I'm looking for a power on 10 as a base that would result in 10,000. Change it to exponential form, drop out the log, 10 to the x equals 10,000. Rewrite 10,000 as the same base, so I can drop the bases out. 10,000 is actually 10 raised to the 4th power. The bases drop out since they're equivalent. X equals 4. 10 to the 4th power would produce 10,000. All right, problem 7. 4 to what power is 2? Well, I'm decreasing if I'm going from 4 to 2. 4 to what power is 2? Well, my power can't be higher than 1 because my answer would be bigger than 4. All right, using the same strategy, set that equal to x, change it to exponential form. Okay, well, I can reduce 4 to a power of 2, so 2 squared is 4, but I still have to raise that to the x power. All I did is rewrite 4 as a power of 2. Okay, this is 2 to the first power. Okay, let's do some properties of exponents here. I know that I can multiply these two exponents together. So this is really 2 raised to the 2x equals 2 to the first. Same bases, they'll drop out. 2x equals 1. Divide both sides by 2. The exponent is a half. Think about that for a second. 4 raised to the 1/2 power is 2. And remember, 1/2 is actually the square root. So it's changing 4 to the square root of 4, and yes, that's true. Square root of 4 is 2. Okay, problem number 8. 10 to what power is 1 over 100? Well, I know 10 squared is 100, but if 100 is in the denominator, it can't be 10 to the 2. It has to be 10 to the negative 2. My work will support that. Set this log expression equal to x. Change to an exponential. We want to get a base of 10 to equal this base of 10 over here. 100 can be rewritten as 10 squared. Pull 10 out of the denominator, adjusting the exponent to negative 2. Same bases, x equals negative 2. Continuing that work over here with number 9. I can rewrite 32 as a power of 2. 32 is really 2 taken to the 5th power. Same base, x equals 5. Number 10, 3 to what power is 1? 3 to what power is 1? To get an answer of 1, I need to take a base to the 0 power. The work that supports it is right here. We just have to understand in here that we'll never get the same base, but if x is 0, we will get the result of 1. So far, in 10 examples, I haven't had to pick up my calculator. I can confirm with my calculator, but I haven't had to pick it up to find an answer. That's going to change in number 11. 10 to what power will give you an answer of 1/3? I could never get the same base of 10, so actually this isn't even going to help me to change it to exponential form. I should have a calculator in my hand. Alpha window, axis number 5, dump in the 10 for the base, the 1/3 for the value. The result is negative 0.47712. I might suggest stop the video, find that template, evaluate, confirm that you're able to use the right template to get this answer. All right, number 12. 10 to what power is negative 2? Is there any way I'm ever going to be able to take 10 and raise it to a power and get a negative answer? Even if I raise 10 to a negative exponent, that just makes the answer smaller, never negative. So this isn't really going to help me, like in the previous example. So I'm going to go to my calculator, alpha window, choose option 5. You're going to get non-real answer. No answer. No solution, circle with a line through it. There's no way you can take 10 and raise it to any power and get the result to be a negative number. I encourage you to, again, stop the video, do alpha window, option 5, dump these values in, and see that your calculator reports a non-real answer. Hang in there, 4 more. Okay, notice how things have changed right here now in the last 4 problems. Notice that, well, at least with 3 of them anyway, I have a log on both sides of the equation. This is property 4. All right, I have a log base 3, a log base 3. These two undo each other. They drop out of the problem. So the result is just that x equals 7. Log base 6 with an exponential of 6, same base. These two will drop out, so x must equal the exponent of 5. 15, same base of log 4. So x equals 2 to the negative 5. That's the answer, but you should really clean it up. Make the negative exponent positive, 2 to the 5th. Compute 2 to the 5th. 2 to the 5th power is 32. Okay, 16, same base, 9. Logs drop out. Solve the resulting equation. The answer is 3. So in this video, we changed forms from exponential to logarithmic and vice versa. We looked at some log properties and we evaluated some log expressions.